Today we start the second unit, and the first topic in the second unit is about the multi-component distillation concept, and in which we are going to learn about equilibrium data, simple equilibrium data, and vapor liquid equilibrium for the multi-component distillation. So we all know the meaning of the binary component. Binary component means when there are two components in the feed, that is called the binary component. Ternary component, there are new term ternary component. It means that if there are three components in the feed for the distillation, but suppose if there are more than two components, 3, 4, 5, 6, they all are come in a one simple group. That group name is a multi-component. So multi-component means the mixture having more than two components. It can be 3, 4, and 5, and 6, 7, and so on. So basically the multi-component distillation means the distillation where the mixture having more than two components, maybe 3, 4, 5, 6, so on. So that is the concept of the multi-component system. Since we know that only top and bottom are the products from the distillation column, so for the two components we need a one tower, one component from the top, one component from the bottom. That's a simple one. But for the three components we need a two towers. Means in the in one tower only one product will be recovered as a pure one, and the remaining two component can be recovered from the second tower. So two towers are required. Similarly, for the four components, three towers, and so on. So in the general format, for the n components, we need a n minus n tower, n minus 1 tower for separation of the components into the individual constituents. So for example, if there are 5 components, so we need 4 towers. The second thing, sequencing of the tower. Sequencing means which there are 5 different towers. So in the first tower, what will happen? How much material will be, which material is separating out from the tower 1, which is from tower 2, and so on. This is called the sequencing of tower. Normally it is a part of the process integration. This is not to discuss here. So that's why just simple summarize it. For example, this is the 4 components A, B, C, D. So in the 4 components we need 3 towers, tower 1, tower 2, and tower 3 to separate into the individual products like A, B, C, and D. So this is a one configuration. You can have a different sequence of the tower. So there are multiple configurations for the separation. So there are so many criteria and parameters for selecting this sequence. But we are much concerned about the multi-component distillation, how this distillation is carried out. So what should be the designing calculations? So as we have discussed about earlier in the distillation column, that for any calculations means or for any designing of a distillation column, the first thing what we need is the equilibrium data. So in the binary system we have gone through the TXY data, but in the multi-component system it is not possible because there are multi-components. So we cannot draw a multi-component distillation data TXY in the XY graph. So how we can get the informations? We can get the informations from saturated liquid calculations and saturated vapor calculations. These two values are very much helpful in the multi-component distillation. The second thing that we require is the operating line calculations. So in the operating line calculations, basically the material balance or the energy balance is the base for the operating line calculations. So these two things are needed, required for the calculations and for the designing a multi-component distillation system as well. So there are two broad methods for the solution for the calculation. The first method is called as a stage to stage calculation. So it is obviously a trial and error calculations. The first thing, it is not an easy one. It is required the rigorous calculations, and that's why we need a computer for this rigorous calculation. and normally the Thiele and Getze method is very popular in the stage-to-stage calculations. And there are a second method for the designing of distillation column for multi-component distillation is a shortcut method. In the shortcut method, we can perform some calculations even in the classroom also. So we are going to select the shortcut method for doing the calculations with simply by calculators, and manual calculations are also possible using the shortcut method. Obviously, shortcut method gives a more error as compared to the stage-to-stage calculation, but we can it can be tolerable. You can say for the preliminary study, it is okay. Shortcut method. So now come to the first one, that is equilibrium data. So normally for the ideal system, we always look for the Raoult's law. It defines for the equilibrium data. So equilibrium vapor liquid composition can be calculated with the help of the vapor's Raoult's law, and we all know this equation, partial pressure of A is directly proportional to the vapor pressure of A and the composition of A. Similarly, partial pressure of B, if there are suppose 4 components, partial pressure of C is a multiplication of vapor pressure of C and composition and so on. And then you can also go on through this equation. This is called the Dalton's law, where the molar fraction of the A in the vapor phase is equal to the partial pressure of A divided by total pressure. And if you replace this partial pressure by this equation, you will get the relationship between the XA and YA with the total pressure and the vapor pressure of A. So similarly, this is for the composition of B, composition of C, and composition of D. So in this way you can find out these basic calculations. But this relation, if you see this total pressure, PA divided by P, PB divided by P, PC divided by P, PD divided by, this is a very informative value, because this is we taken this constant value as a Ka, Kb, Kc, and Kd. For example, for the first case we can take in this value as a Ka. In this case it is taken as a Kp, Kb, here Kc and Kd. So this is a very informative and very valuable data, and this information is called the vapor liquid equilibrium or the vapor liquid distribution coefficient. So this K is denoted by this one. Ka is the vapor liquid distribution for A, Kb vapor liquid distribution for B, and so on. So basically this is one of the very important thing to know, what is the meaning of vapor liquid equilibrium or the vapor liquid distribution coefficient. So normally these are the two very common and very famous value for the K, and it is a function of temperature, pressure, and composition. So it means that if you change the temperature, if you change the pressure or composition, the K value will be different. But normally what happens, we can assume that for the lighter hydrocarbons especially, we can assume that it is not a function of composition. So only it is a function of pressure and temperature. And further we know that for the ideal system, this value can be written K is equal to Pi for the any component, ith component, vapor pressure divided by the Pt. This formula is very useful for calculation of the K, and this K is even calculated when the pressure is constant. In fact, if you see here, if the pressure is constant, so K is simply a function of temperature. This is a nomograph where the temperature and pressure, both variables, are given here. So changing the pressure and temperature, you can get the value of K for particular components. These are a few components like methane, like ethylene and ethane, propane, propylene. All these lighter components are given here. So they all, the respective of the composition, they can be find out for the particular pressure and particular temperature. So this is a temperature curve, and this is the pressure curve, and these are the lines for the K values at any given temperature. For example, this is the temperature and this is the pressure. If you just draw a line for pressure and temperature, so all these cut points are the K value for this temperature and pressure for that components. In this way we can get the K values for different materials. So what is the importance of these K values? These are very much useful for the calculations in the multi-component distillation. So before going into the details of multi-component distillation, let us know about the key component concept. So there are two, basically the concept of two components. One is light key and one is a heavy key component. So light key component and heavy key component, these two are the components in the multi-component distillation. So what is the meaning of light key? Light key means it is a lighter in nature. So normally lighter in nature means in the distillation column, the light will be always in the distillate and heavy will always be in the bottom. So which is present in residue in important amounts, while the components lighter than the light key are present only in a very small amount. That is a concept of light key. What it means that if all the components are present in the residue at important concentrations, the most volatile component is taken as a light component. So light component definition is based on the residue. Similarly, heavy components normally they are present in the much more amount in the bottom section, but their key component definition is based on the distillate. So present in distillate in important amounts, while the components heavier than the heavy key components are present only in small amounts. And similarly, if all the components are found in the distillate at important concentration, then the least volatile is the heavy key. So this is the concept of the light key and heavy key, and they are very much useful. For example, if suppose there are so many components like A, B, C, D, E, F, so how we can get the key components? First, what happened? We have to list out all the components in order of their relative volatility. A, B, C, D, like this one. So suppose A is the most volatile component and F is the least volatile component in our system. So components lighter than the light key. Suppose C is the light key. So all the components lighter than the light key is called the light components. So in this case, A and B is the light components. And suppose D is the heavy key. So all the components that are heavier than the heavy key is called the heavy components. So in our case, C and D are the key components, and A and B is the light components, and E and F are the heavy components. So this is the way to define and to understand what are the key components and what are the light components and heavy components. Thank you very much.